How do you do? How do you know which double bond reacts first? And then there's another. Oh, that's weird. What's up there and what's here is different. Okay. Huh. That's one of the part of the question. Okay. And then the other part is show an example where the thermodynamic, I'm just going to say T because it's such a long word, and kinetic products are the same. And I actually typed this up, and then I threw it on the OneDrive, okay? But I forgot to put the questions in the document, so I'll have to update it. So the molecule that we're going to deal with is this one, actually. And it's from that problem. And the question is, first question is, how do you know which double bond reacts first? Because you have two, right? And we were talking about this the other day, and there's something I couldn't remember. So I had to go back and actually had to go look at my notes. And the answer has to do with this. Whenever you attack one of the double bonds, you're going to have resonance structures. And whichever has the combination of most stable resonance structures is the one that gets attacked first. Okay? So let me draw that for you, what that means, okay? So first thing I'm going to do is I'm going to label these things A, B, C, and D. And what I want you to recognize is when, like, you use HBr with this, for example, HBr is everybody's friend. The HBr could add at A, B, C, or D, right? So if it adds to A, for example, then what you'll end up with is this. Oh my gosh. Sorry, this thing is just being ornery. I'm having a hard time drawing. So that's H. I'm going to call it A. Where's the carbocation? And you can go, yeah, it's on B, where B is here. So that's where that's going to be. So that's the positive charge. Now you can see that this has resonance structures, right? And in the resonance structures, I'm not going to draw all the arrows because it gets really messy. But you end up with that. Go ahead.
Why does the H go
Oh, I'll talk about that. That's part of the figuring it out. Because if it adds to B, right, that's another option. And then the carbocation will be at A. So hang on. So I'm going to go through each one, and we're going to analyze each one and talk about, like, what makes this a better position to add the hydrogen. Okay? So then if I do B, then it's the Markovnikov, right? And so I get a positive charge there, and then I get the hydrogen here. So that's hydrogen on B. Like that. Does it have a resonance structure? No. Because, right, the positive charge separated by now an sp3, there's two hydrogens there, sp3 carbon, so there's no delocalization of this double bond, so it becomes isolated from the charge. Remember we talked about different kinds of double bonds. There's conjugated, there's isolated, accumulated. This becomes an isolated system where you have the carbocation isolated from the double bond. That's a lot less stable. Remember the whole REO thing, resonance is a very important factor in determining stability. So right away, that eliminates B as a possibility, right, as where it adds, even though it doesn't follow Markovnikov's rule. But Markovnikov's rule, the way we learned it, it has to do with the most stable carbocation forming. So this carbocation in A is more stable than the carbocation in B, okay? Because of resonance.
Just to reiterate, because I was on the test as well, secondary resonance stabilized
Is more, it was radical, but yes, is more stable than tertiary. Yeah, it's true for carbocation. And if you remember, well, it's not as clear in carbocations, but if you remember, there's a table that I put in the slides. I know it's one slide out of hundreds, okay. But there's a table I put in the slides on radicals that I inserted that the book didn't have, and it showed the stability of radical with resonance versus radical tertiary, secondary, and primary. And the ones with resonance were like, I just drew them at the top of the chart, way up in the top in the middle, because they're a lot more stable. Okay. Okay, so let's talk about what happens if I put one at C.